Hello and welcome back. In this video lecture, I'm going to discuss section 1.5, which is on solution sets of linear systems. Okay? So the first thing we're going to discuss is the difference between a homogeneous system and a non-homogeneous linear system. Okay? So this is not only important in linear algebra, but this concept also appears in differential equations. So if you've taken a course on differential equations, then you're probably already kind of familiar with this. As I mentioned, it does show up in various mathematical courses, such as linear algebra and differential equations. And then from there, we're going to describe the solutions of a homogeneous linear system. So we're going to talk about this with an example, and then we're going to talk about the connection between the concept of span and a homogeneous linear system. So remember, the concept of span was discussed in two sections before. So in section 1.3. And then we're going to look at the geometry of the solutions for this kind of system, okay? For AX equals to B, this matrix system. Okay, so let's go ahead and define what a homogeneous linear system is. Okay, so a system of linear equations is said to be homogeneous if it is in the form of AX equals to 0. Okay, so you have your coefficient matrix here. Okay, you have your solution vector. Okay, and on the right-hand side, you have your 0 vector. Okay, okay, so A here, right? So A belongs to, right? We're assuming that A is in an M by N matrix. Okay, so M being the number of rows, N being the number of columns. Okay, so let me write that a little bit bigger. All right. Okay, and we also know that 0 is the 0 vector. And the 0 vector has to be in R of N. Okay. Okay, why is that? Well, based on what we discussed before, okay. Right, so if A is an M by N, okay, and X, right, X has to be an N by 1, right? Remember, to multiply a matrix with a vector, these values have to be equal. If they're not equal, this is not doable. Okay. And the result, right? The result of this is going to be M by 1. Okay. So in fact, the 0 vector should be, so based on this, should be R of M. Okay. So R of M. Okay. Right. Again, this is A, right? This is your matrix A. This is your solution vector, right? And this is the vector, 0 vector in this case, which basically consists of, or the entries of the 0 vector are all 0. Okay, so there's 0, so there's basically M number of zeros in this 0 vector. Okay. All right, so that is basically, that is what a homogeneous linear system is. Okay? Okay, that's what it is. All right. Okay. All right. So then, okay. So one thing to observe here, okay, is that the system this system that we're discussing here, okay, it always, right, it always basically always has a solution, right? And you can see that if you let x be 0, then you get, right, the matrix times the 0 vector will give you back the 0 vector. So this always has, right, this always has 0, right, as the solution, right? The 0 vector is always a solution to that, okay? Always has at least one solution. Okay. And that is, okay, that is what we call the trivial solution. Okay, again, if you're currently taking, or if you've taken differential equations, then this is this, then you should be, you should recognize that, okay? Because this concept is also used in that, in differential equations, okay? All right, okay. So the question is, all right, well, actually, so the question is, let me back up for a minute. So the question is that the only solution? So in other words, is this 0 vector the only solution? And the answer is, it depends. It will depend on the makeup of the vectors that are in this matrix A, okay? And that's going to be further discussed in section 1.7, okay? Okay, so let's continue on here. Okay, so one thing that arises from this, okay, is that, okay, the system has a non-trivial solution, meaning that, right, that not only is x equals 0 a solution, but it can, right, it may happen that there may be another solution. And this is the condition under which that will occur. Okay, so ax equals 0 so this non-homogeneous system has a non-trivial solution if and only if, that's what that means, if and only if the equation has at least one free variable. Okay. All right, very important here. Okay. So again, this isn't, right, this means that you can go in either direction. Okay. So with this, right? So again, if this has a non-trivial solution, so meaning that a solution besides the 0 vector, okay, if that's the case, right, if it has a non-trivial solution, then the equation has at least one free variable. Okay. All right. Now, what does that mean? Okay, so what this implies is that, let's say here's your, right, so here's your system. Okay, let's assume that that the coefficient matrix is a 3 vector. Okay, and also assume that it's an echelon form. And let's say, right, we get this, okay. Right. So again, the asterisks are basically just denote that they're numbers besides zero, okay, in this case, okay. So you have a matrix and you go through the row operations and you put it into echelon form, and this is what you end up getting, okay. Now look here, so right here, okay, this indicates, right, that we have one free variable, okay. So again, you have x1, x2, and x3. So x3 turns out to be your free variable, okay. Furthermore, okay, since x3 is a free variable, remember that x3 could be, you can choose x3 to be any value. So in that case, that tells you a structure like this, right? A system that has this kind of structure will have an infinite solution set because of that free variable, okay? So that's what this is saying, okay? So not only does this, by the way, it should be, since we're talking about homogeneous system, okay, then these have to be zero. Okay? So not only does the zero vector satisfy something like this, but there are also other solutions, okay, all right, because of that free variable, okay. Now we can go the other way, right? If you have a system like this, right, if your equation, if your linear system has one or has at least one free variable, then that means, right, that there has to be a non-trivial solution. Okay, so it works both ways. Okay. All right, so let's demonstrate this with a specific example. Okay, so that way you can think about this more. All right, so let's take a look at this example. Okay, so let's determine. So determine if there is. Okay, determine if there is a non-trivial solution. Okay, so here's our system. So we have 3x1 plus 5x2 minus 4x3 equal to 0, minus 3x1 minus 2x2 plus 4x3 equals to 0, and 6x1 plus x2 minus x3 equals to 0. Okay, let's just double check my signs here. Okay. All right. Okay, so this is an example of a homogeneous system, right? We have three equations, okay, and there are obviously three unknowns, and their right-hand side, there's your zero vector, okay. Right. Okay, so to answer this question, right, to determine if there's a non-trivial solution, what we need to do is we need to basically write the matrix form of this, and then go through and then put that into echelon form, and then see if we get a free variable or not. Okay. So let's do that. All right, so we're going to get our system here. So we have 3, okay, minus 3, 6. Okay, again, first column for x1 coefficients. Second column will be for the coefficients of x2. Okay, so 5, -2, and 1. And then the third column will be for the coefficients of x3. And then I'm going to go ahead and augment the zero vector on there, even though it really doesn't matter because when you apply the row operations, these are still going to be zero, obviously. Okay. All right, so there's our augmented system. Okay. So again, the details of the row operations are in the notes. Okay. So we're going to put this into REF form. The notes can be accessed, or I should say the notes are in the YouTube description. Okay. All right. So going through this, okay, we end up, and let's go down here. This is what we end up getting. So we have 1, 0, minus 4/3. So 0, 1, 0, and then the last row should be 0. Okay. And then we have 0 here. Okay. All right, so obviously, so we have our answer now, right? Okay, we have our pivot here and here, but right here, we definitely have a free variable. So x3 is our free variable. And that's all we need to know, right? Because then we can use this theorem, right? Okay, so because there's a free variable, that implies that this system must have a non-trivial solution, okay? Right. So let's go ahead and find that. That'll be a good review from the previous material in this chapter. Okay. All right. So x3 is a free variable. So that means that we need to assign this to some variable. So let x3 be equal to, let's say, t, where t is some real value. Okay. Now, again, I'm using this notation because this is a more formal way to do it. It's kind of it's a good habit to get into now. You should always, when you're assigning your free variables, you should always use a different letter. In other words, you don't want to use this, you don't want your solution to contain the same variable. It's it's not that it's not that good actually to do this. All right. It's better, like I said, it's just a more formal way. And also later on in a more advanced course, this is how they're going to approach this kind of concept. Okay. All right. Okay, so in any case, there's our free variable. Okay. So now with that, we can define our solution vector. So let's do that over here. I have some space here. Okay. So x3 is t. Okay. So that means looking here, okay, we're going to get x1. So, well, let's back up. Let's see what x2 is. Okay. So x2, that's the coefficient for x2. So that means that x2 has to be 0. And x1, that's the coefficient for x1, and then you have minus 4/3 times x3. Well, x3 is t. And so therefore, x1 obviously has to be 4/3 t. Okay. So that, again, this is what I mean, that you should, it's not a good habit to say that x1 is equal to 4/3 times x3 because you're already using it as a variable here. So it's a good habit to change this and to basically assign this to another variable. Okay. Okay. In high school, maybe that's acceptable, but at college level, this is definitely, or I should say, yeah, at college level, this is more suitable. Okay. All right. All right. So in any case, here's our solution vector. Okay. So we have x1, x2, x3. So x1 was 4/3 t. x2 is going to be 0, and x3 was t. Okay. All right. Okay, so we can go ahead and write it in what's called parametric form. You can do that by factoring out the t here. So we get 4/3, 0, and 1. Okay. Okay. So what we have here, okay, basically what this is saying, okay, is that if you choose, right, if you let t be any value, right, any real value, and you multiply it with this vector, then that's going to be, right, that's going to be a solution of this system. And notice, right, notice something. If you let t be 0, right, then you're going to get the 0 vector, which is, right, which is the trivial solution. Okay, so for these kind of systems, right, for this homogeneous system, the trivial solution is always there. Okay, right. And in this case, we showed that we get more than just a trivial solution because of the free variable here. Okay, so geometrically, what we have here is basically a vector that's going through the origin, right? Because the origin is the 0 vector. Okay, right. And also going back to the span, right? Going back to the span idea, we can say that x, right? Well, the solution vector belongs to the span of this vector. Okay, so we can write that over here. Let's see if I have some space here. The span of, let's call that V, where V is this. So remember, that was an idea that we discussed in the in these 1.3 lecture video. Okay. So again, what this means is that you, for all the solutions, right? So this is a compact way of just saying that all the solutions of the system are a multiple of this vector. Okay, this is what this is. This is basically just a, so your solution forms a scalar multiple of this vector. That's what that means. Okay? So that's a compact way of representing this. Okay. All right. Very nice. Very nice. Okay. Okay. Let's see. Let's look at another example here. Okay. All right. Let's do that here. Let's see. Okay. All right. So by the way, remember that, right? If this vector is the 0 vector, that's a non-homogeneous system. Okay. If this vector B is non-zero, okay, then it's called a non-homogeneous system. Okay, that's the difference. Okay, that's the difference between the homogeneous and non-homogeneous. Okay, so that depends on, right, whether this vector is the 0 vector or not. Okay. So let me just Okay, I can summarize, or I can write that here. Okay, so it's homogeneous. Okay. If that's the zero vector. If the vector B is not equal to zero, then this is a non-homogeneous system. Okay. Right. So very important idea, very important concept in mathematics, especially in linear algebra and in differential equations. Okay. All right. Let's look at another example here. So let's say we want to describe all solutions of the homogeneous system. Okay, so we have we have basically one equation, but this is still by definition a system. Okay, so a system can basically be, it could be one equation or it could be more. Okay, so we have 10 times x1 minus 3 times x2 minus 2 times x3 equals to 0. Okay. All right. So what we need to do here, the first thing we should do is to basically write this as a matrix. Okay. So let's do that. Okay, so we have 10 minus 3, negative 2, and there's our 0. Okay, since we have 3 variables here, then obviously our matrix, right, should be a 3 by 3. Okay, so we're going to have 0 here, sorry, 0, 0, 0, 0, and then 0, 0, 0, and then finally 0. Okay, so we have a column for x1, a column for x2, and a column for x3. So if you have 4 variables, then obviously you're going to have a 4 by 4 system. Okay, so there's the matrix system that represents this. Okay, all right. So it's already in, pretty much it's already in, it's not quite in reduced row echelon form, but it is in row echelon form. So we can go ahead and work from here. Okay? And notice that we end up getting, right? Obviously we have 2 free variables here. Okay. 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 Again, over here, right, same idea. We have x1, x2, and x3, we have a 0 here. So that's a free variable by definition. Okay, so there you go, free variable. Okay. Okay, so our free variables are x2 and x3. Okay. So let's go ahead and assign our variables to that. Okay. So I'm going to assign x3 to, let's see, just to be consistent with what I have in my notes. I'm going to assign x3 to be equal to t1. Again, you can use whatever notation you want as long as it's not the same variable here, okay? As long as you're not using the same one. Okay? And then for the other one, we're going to let x2 be t2. So t1 and t2 both belong to real values. Okay, so that means for x1, okay, so we have 10 times x1 minus 3 times x2 minus 2 times x3 equals to 0. Okay, so we know x2, right? Right, x2 is t2, x3 is t1. Okay, so when you're doing this, right? Okay, when you're doing these type of problems, make sure, right? Make sure you define these properly, right? Okay. Okay. Okay, so let's solve for x1. So x1 is going to be, we're going to have, so we have minus, or actually 3/10, 3 over 10 t2, and then plus 2 over 10 t1. And I'm going to go ahead and reduce this. This becomes 1/5. All right. Okay, so now let's write out our solution vector. Okay, so x1 is this. x2, okay, x2 is going to be t2, right? And x3 is t1. Okay. And again, the important thing here is that whenever you have a free variable, your solution vector is always dependent on that free variable, just like here and just like this one here. Okay. So we can go ahead and write this in what's called vector parametric form, just as we did with this one. Okay. Okay. So let's first we're going to take out. Let's see, we're going to have t1 here. Okay. Okay. Oh, okay. You know what? That should be, sorry. T2. That's T2, and this is T1. Okay, there we go. Yeah, so 3/10 T2, and then plus 1/5 T1. Okay. All right, so T2, T1. All right, there we go. All right, so this, right, we have here, right, x2 is T2, and x3 is T1. Okay, there we go. Now, we're going to get T1. So T1, we're going to have 1/5, okay? 0, and then 1, right? Because there is no T1 here, and then T2, right? We're going to get 3/10, 1, and then 0. Okay. some space here. Okay, patience is a virtue. All right. Okay, there we go. There's our solution vector. Okay, and notice that our solution vector, okay, depends on two vectors now. Okay, so what we can do here is we can let, right, we can let this one be V, let this one be V1. Okay, so let's call this V1, and let's call this V2. Okay, and then, so we can say that X now, right, so X belongs to the span of V1 and V2. Okay. So again, what this, going back to the concept of the span idea, any solution, right? Okay, right? Any solution of this system, okay, can be written as a linear combination of this one and this one. Okay. In fact, what this is saying is that the solution of this, okay, if you've taken Calc 3, then you, or even if you've in pre-calculus, right, this is just the equation of a plane, which is described by this, right? You have these two vectors, right? Right. So let's say this is V1 and this is V2. They're both, right? They both have the zero vectors here. They're both in different directions, as you can see. By the way, this vector, if you're thinking about this geometrically, this is being X, Y, and Z. This vector lives in the XZ plane, right? And this vector right here lives in the XY plane. Okay, so you have, let's say this is like one vector, and then you have another vector like this. Okay, so you can imagine all the, right, all the linear combinations of these vectors, which is what this is saying, is a solution to this homogeneous equation. Okay, and that is the same thing as saying this. Okay, right. Okay. Okay, and just to kind of write down what I said there. So this is a vector, right, that lives in X, in the XZ plane. And this is a vector that lives in the XY plane. Okay. So now when we go, once we get beyond, right, once we get beyond 3 dimensions, then we won't know what, we won't know what's going on because it's impossible to see beyond 3 dimensions. Like I mentioned before, it's the best you can do, the best we can really do is take something from, is to basically take something from 4 dimensions projected onto 3D. Okay, and even that has some issues. Okay, so again, when you're learning linear algebra, sometimes the geometry is not too important. The concepts, right? Understanding how things work conceptually is more important because that idea will, right? Those concepts will expand beyond 3 dimensions. Okay, whereas the geometry basically only gets us so far. Okay, especially in the higher level math courses. Okay, but at least for now, right, we're able to kind of visualize what's going on. Okay. Okay, so let's see. So let's So based on these two examples, I'm gonna write out, we have a conclusion here, okay? All right, so let's summarize what we have. So the solution set of AX equals to 0, okay, can be expressed as the span of your of the vectors that are involved. So V1, V2, V of n. So for example, right here, right? So this, the example we did earlier here, okay, we can represent the solution vector in this form. Same thing over here, right? The solution vector can be represented as the span of these two vectors, okay? So we can generalize this, okay? So the solution set of your homogeneous system can be expressed as a span of the collection of vectors that's forming them. Okay, so if the only solution, solution is the zero vector, then okay. So if it's only this, if it's the right, if the solution is the is only this zero vector, okay, then the solution set is represented by this. It's just a span of 0, right? That makes sense because you have just that vector in there. So any multiple of that vector 0, right? So, any number times the 0 vector will be 0. So it's just a span of itself. Okay. So that's pretty trivial there. Okay. If this system, if this homogeneous system has only one free variable, then okay, the solution set, okay, then the solution set, okay, is basically a line through the origin. That's what we observed here, right? Okay, there's only one free variable, okay? There's only one free variable, and right, so therefore, right, that vector is basically a vector that goes to the origin. Okay, right? This is right, so we said that. Okay, remember that. Okay, from here we had x belongs to the span of V. Okay, that's what's right. That's how we can describe this. Okay, so every solution vector goes through every vector in this set. Okay, so again, this is just a set, right? Every solution in here goes through the origin. Okay, all right, all right. Okay, third. Okay. Okay, if this non-homogeneous, sorry, if this homogeneous system has two or more, okay, free variables, okay, then